All right, physics students, today we're going to talk about color and polarization. And again, everything that we look at, we see different colors. Some people don't see as many colors as other people, but the point is everything we see is light that is reflected off of different objects. If I turn off the lights and I'm in a completely dark room, I can't see anything because there's no light entering my eyes and there's no way for my brain to make sense of no information. So explaining in a dark room, you know, that something is blue, I mean, we remember that from what we've seen before, but if we didn't have that context, we wouldn't be able to process that. So the colors we see, like I said, are the reflected wavelengths. So the light that we see coming from the sun or coming from light bulbs is typically white light, which is made up of all different colors of light. And the objects that we look at have different tints and dyes and paints on them, and all of those things absorb most of those wavelengths and reflect back to us what we see. So if I'm looking at a blue wall, white light is shining on that blue wall, but only the blue light wavelengths are reflected back to me. Here's another example. Here's a green leaf. You've got all of the light from the sun coming here, reflecting off green light. Now, notice that it doesn't show a white light hitting it. It shows red, green, and blue. Those are the three additive primary colors. All colors that we see are made up of those three colors. So yes, there is orange light and yellow light, but those are mixes of red and green. And so the red and green light here are getting absorbed by the leaf only. I'm sorry, the red and blue is getting absorbed by the leaf. Only the green is able to come off. And so I mentioned that red, green, and blue are our additive primary colors. And again, if you think back to art class, even when you were a little kid, you were told that the primary colors were yellow, blue, and red. And those are what we call subtractive primaries, and we'll talk about those in a second. But additive primary colors, red, green, and blue, are the colors that our eyeballs are sensitive to. And we combine those colors in different ways to make the different colors that we see. You can see that when all three colors are mixed together, you get white right here in the center. When red and green mix, you get yellow. When red and blue mix, you get magenta. And when blue and green, you get blue-green, also known as cyan. Now, these are the three colors. If you get your eyes right up to a TV screen, you can see these different pixels. And they come in various shapes, but again, they're all just mixing red, green, and blue light. I'm not going to show this video here, but if you'd like to go on to YouTube and look at that, you can see how pixels came to be from the earliest televisions. It's about 4 minutes long. All right, so then we get to our subtractive primaries, and these are the colors that you are most familiar with when it comes to art class. So you've got cyan, yellow, and magenta. Now notice these were all the secondary colors that we had on the additive primaries. The secondaries here are red, green, and blue, just like what we had. Now the difference here is when you mix them all together, you don't get white light, you get black light. And that's because subtractive primary colors are subtracting the wavelengths out. And so if you subtract all the wavelengths out, you're left with nothing, which is the color black. Next, we've got polarization of light waves. Now, this is a little bit hard to visualize, but maybe some of you have polarized sunglasses. But light, think of light waves as those little packets of transverse waves. And sometimes you got waves oscillating up and down towards you. Sometimes you've got them going side to side. Sometimes you've got them going at some oblique angle. And a polarizer is something that filters out all light except for light that's oriented in one particular direction. So I can take a polarizing filter, and again, these filters, they can look just like glass, and it will only allow one particular plane of polarized light through. Now, if I take two polarizing filters and I put them at cross paths to one another, they will block out all the light. Now, again, this seems a little bit abstract to you, but we're just kind of getting you familiar with some of these words. This video here shows light coming in from all different directions. And you've got 3 different rings here. Now they're going to put a polarizer in one of them, and notice that this jumble of waves gets oriented. All right, and then they put a second one on, and when they rotate that one at 90 degrees to the first one, it blocks out all of the light. Now here's the crazy thing. If you put a third one in the middle and these 2 are at 90 degrees, it actually will cause the light to change and transmit even through that last one, which is sort of bizarre. But that's quantum physics for you. All right, now flat surfaces polarize light. So the hood of a car, the surface of a lake. You've got, again, all this light here that is oriented in every direction. Once it hits, only one orientation comes off. Now, if I'm wearing sunglasses that are polarized, I want vertically polarized sunglasses to block this reflected light. It doesn't mean I'm not going to be able to see anything. It just means in that exact direction, all of that light is going to get reflected away, or I'm sorry, filtered out, because what that typically shows up as is glare. So if I'm looking at a lake and the sun is beating down and all I see is kind of a wash of light, the polarized sunglasses can filter out some of that glare, or it can filter off the glare coming off the hood or windshield of an oncoming car. All right, that's it.